This is the final podcast on Chapter 10 in Zumdahl, a look at liquids and solids. This is phase changes, including a look at what are called phase diagrams. We're talking about changes of state. Now, the graph of temperature versus heat applied, or time where heat is being applied at a constant rate, is called a heating curve. And the temperature at which a solid turns into a liquid at 1 atmosphere pressure is defined as the melting point, and the energy required to accomplish this is called the heat, or the enthalpy of fusion, delta H FUS. If you look at this particular heating curve for water, you see that we have the the pressure across the bottom and the temperature on the y-axis. It's not labeled very well, but it gets the point across. In the first instance, below zero, water is an ice. When it's flat, you have water and ice. Then the next rise is water, water and steam, and steam. Well, it turns out that 1 over the slope is the heat capacity of the material. In this case, it's water. You'll notice that the heat capacity of liquid water is about twice that of both ice or steam, and that in fact is true. So, in the space there where the line is flat, as we're adding heat, the temperature is not rising, so the added heat is causing the ice to melt, and that value is the heat of fusion. The next flat line area is the heat of vaporization, because as the heat is added to water at 100 degrees, the liquid does not get above 100 degrees. Instead, that heat is being used to vaporize or overcome the intermolecular forces of attraction. Melting point. Melting point is determined by the vapor pressure of both the solid and the liquid. Yes, solids have vapor pressure. In fact, at the melting point, the vapor pressure of the solid is equal to the vapor pressure of the liquid. Let's look at some examples. Here we have a couple of flasks connected by tubing. We have solid water, called ice, but solid water on the left and liquid water on the right. And there is water vapor in the entire system. Now, if the vapor pressure of the solid is higher than that of the liquid, the solid will release molecules in an attempt to achieve equilibrium. And those molecules will condense into the liquid water. This can only happen, though, if the temperature is above the freezing point, since the solid is releasing its molecules and they're becoming a liquid. If the vapor pressure of the liquid is higher than that of the solid, the liquid will release molecules to achieve equilibrium, while the molecules condense to be a solid. What's the temperature here? Right, the temperature must be below the freezing point of the solid, since the liquid is turning into the solid. If the vapor pressure of the liquid and the solid are equal, then the solid and liquid are vaporizing and condensing at the same rate. We're at the melting point. Boiling point. Well, when a liquid boils, the vapor pressure of the liquid equals the external pressure above the liquid. Normal boiling point is the boiling point at 1 atmosphere pressure. Now, you might have superheating. That is, you can heat it above the boiling point, and that sometimes has been known to happen. You can also have supercooling, by the way. I know it's not related to boiling point, where you can cool something below the freezing point. Now, phase diagrams. Phase diagrams are a way of looking at temperature versus pressure for a closed system and a series of lines indicating where there's a phase change. Here's one, if you look at it. We have temperature on the horizontal axis, pressure on the vertical axis, and you notice 1 atmosphere runs through the middle. Well, if we take a sample of the material as a solid at a pressure way below 1 atmosphere and raise the temperature, it will move directly to the gas phase. We say it sublimes. This is the sublimation process. And indeed, freeze drying of foods is done this way, so you don't end up having to do it at a very, very high temperature. You simply drop the pressure. Here we have the solid becoming a liquid, sort of normal melting, although the pressure is a little bit below 1 atmosphere. And here is boiling. Our pressure of the system is a little bit above 1 atmosphere, but as we raise the temperature, the C moves from this liquid to the gas phase, meaning the material is boiling. It's also possible to do it by raising the pressure. If you raise the pressure, D goes up to the D up top. That is a gas becoming a liquid by raising the pressure, and that is how things like propane gas are liquefied for use in a gas barbecue or to power a Zamboni. You have two other points on here. This is the triple point. That triple point is the point where the solid, liquid, and gas can all exist at equilibrium at the same time. And then you have a critical point, and the critical point is the temperature pressure system situation where the material cannot exist above it as a gas. This happens to be the phase change diagram for water. The density of the liquid is higher than that of the solid. And notice that the slope of the liquid to solid interface is a negative value. In the case of carbon dioxide, it's a positive value because here the solid is more dense than the liquid. The same system would apply, but notice that 1 atmosphere happens to cross the line at the solid to gas interface. And so by raising the temperature at room temperature, carbon dioxide sublimes, which is why it's called dry ice, because at normal pressures it never becomes a liquid. You actually have to raise the pressure to about 5.1 atmospheres before it could become a liquid. And those are phase diagrams.